right, hello and welcome back, Chem Kings and Queens, to Klaus's Chemistry Kingdom. Today we're going to be looking at exploring the use of molarity with stoichiometry. So we've already learned in class about molarity, calculating the moles from the volume and the concentration of a given solution, but now we're going to take that idea and apply it to what we know about stoichiometry. First, a bit of a review. We know that if we have the mass of substance A and we want to get to the mass of substance B, that would be in grams, we need to convert mass to moles using the molar mass, and then we can use the balanced chemical equation to convert to substance B. And once we know the moles of substance B, we can convert back down to grams of substance B. Notice we could do the same thing with the volume of a gas using PV equals nRT, the ideal gas law. That allows us to take the volume of either gas A or the volume of gas B and convert to moles of that specific gas. But no matter what, the only way that we have to convert from one substance, substance A, to another substance like substance B is to use the coefficients in the balanced chemical equation and convert from moles of one substance to moles of another substance. So in order to convert from one substance to another, we need a way to get to moles. Well, molarity gives us a way to get to moles from a known volume and a known concentration of an aqueous solution. If we have a solution, it's made from some compound dissolved in water. We know the volume of that solution that's easily measurable in the lab. Say we have 20 milliliters of solution, and we know the molarity, say 0.5 molar. We can use that information using the molarity equation. Molarity is equal to moles per liter to calculate the moles. And once we have moles, we can convert back and forth. So let's take a look at an example here. I'm not sure why this moved all the way down to the bottom. There we go. So let's take a look at this example. If 20 milliliters, that's a volume, 20 milliliters of our 0.5 molar silver nitrate solution is allowed to react with excess copper metal, what mass of silver should one expect to produce? Okay, so first of all, this is not a limiting reactant problem. Not limiting reactant. Why? Because it says we have excess copper. So the limiting reactant is silver nitrate. We don't have to determine that. What do we know about the silver nitrate? We know that the silver nitrate solution has a volume of 20.0 milliliters or 0.0200 liters. And we know that it has a concentration of 0.500 molar. Well, I know that I can use this molarity along with this volume to calculate the moles of silver nitrate. And once I know the moles of silver nitrate, I can use the balanced chemical equation to convert to moles of silver, and then I can use, of course, the molar mass of silver to find the mass of silver that I would expect. So let's go ahead and try this. We have molarity is equal to moles per liter. So molarity times liters equals moles. I'm going to come back up here to the top to plug into this equation. The molarity is 0.500 molar times my volume of 0.0200 liters. And that's going to be equal to my moles of silver nitrate. Plug that into a calculator real quick. And we get 0.0100 moles AgNO3. But I'm not done. That's just my moles of silver nitrate. I need to take that and do my stoichiometry. 0.0100 mole of AgNO3. From my equation, 2 moles of silver nitrate produces 2 moles of silver. So 2 mole AgNO3 makes 2 moles of silver. And I need mass, so 1 mole of silver has a mass of, let's see, 107.87, I believe. See, silver 107.87, that's correct. 107.87 grams silver. And of course, we always go through and check. My moles of silver nitrate cancel with my moles of silver nitrate, my moles of silver with my moles of silver, and I'm left with grams of silver, which is the units that I should expect. 0.01 times 2 divided by 2 times 107.87 grams I get 1.08 grams of silver produced. Hope this is helpful. This is just an introductory look at using the idea of molarity, of concentration, to perform stoichiometric calculations. Next time, I'm hoping to make a video using maybe 2 solutions in a double replacement reaction, and we'll look at some limiting reactant problems using molarity.